All right, here is a problem where we need to find the winner on a tic-tac-toe board. Um, and basically, this just goes through the rules of tic-tac-toe. And so you have a sequence of moves which describes a game of tic-tac-toe where the moves are the alternating moves from the two players. And then at the end, we want to see if one particular player has won, or if it's a draw, or if the game could still be ongoing, in which case we return pending. This goes through some examples. So here it's a win because we get the 3 in the row, another 3 in the row. So here the player A, the first player wins, and here the second player wins. This is a draw. They didn't give an example of a pending, but it would just be like, imagine this board, but with any number of these X's and O's missing. Then that would be a draw, or that would be pending. Okay. So we have these constraints here. It's always good to look at the constraints. There is something really useful here. There are no, okay, well that's obvious. Well, this is actually sort of a subset of this, and this is the important one. Moves follow the rules of tic-tac-toe. So, this is really interesting, and maybe this will come. Yeah. So basically, let's first talk about our approach here. What we're going to do. So essentially, what we need to do is we need to reconstruct this tic-tac-toe board, and then having reconstructed it, determine which case we're in, whether we have a winner, or it's a draw, or it's pending. And one thing that's interesting here is that, this is actually an example where you want to be careful about if you're using generative AI to help you with exercises like this. Because I asked this to GPT-4 to get some ideas on different approaches for different solutions, and GPT-4 implemented it in such a way that it checked for these conditions of a win, a draw, or pending after every single move. And that's not necessary here because look, moves follows the rules of tic-tac-toe. So the reason you would want to implement that checking after every move is so that you need to stop the game as soon as you get to a win or a draw. Because you can't keep playing after that. But if you were to keep playing after that, then that would be a situation where moves does not follow the rules of tic-tac-toe. So the fact that moves follows the rules of tic-tac-toe, well, first of all, that means that there are no repeated elements on moves because that would be against the rules. But furthermore, the point that I'm making in the moment is that the fact that it follows the rules means that you only need to check at the very end. Because you don't need to check after every move because you don't need to worry about stopping as soon as an ending condition is met. Because moves will stop. The sequence move, or the list moves will stop as soon as one of those stopping conditions is met. So anyways, we can implement this. And so basically, like I said, we reconstruct the board and then we check for the conditions. Now, I think the straightforward way to do this is to check for, is to build the board as you see here. So actually, like, using the moves, fill in X's and O's. Like, create a board which is a 3x3 matrix, which in Python you usually have like a list of 3 entries, and each of the 3 entries is a list of 3 entries. And that first outer list could represent the first outer list would be the rows, and then the inner one would represent the columns, and then you can use that. But then when you do that, the code for checking the winning conditions is a little clunky, because you need to check if if you get 3 in a row that are a symbol, and you need to check all of them, and you need to check the diagonals. The way that I thought of this in my mind was that because we're doing a lot with matrices, this could probably be streamlined using NumPy. And so that's actually what I did for this, is I did a solution using NumPy. Now, I don't know if you're always going to have access to NumPy, but it's like, like if you're using these exercises to prepare for like job interviews, are all job interviews going to let you use NumPy? They probably should, because NumPy is like ubiquitous in Python programming. But if they don't let you, then you would have to do this sort of like longer process of like building it using X's and O's, and then checking all the all the different conditions and stuff. But I will show the solution using NumPy. So first we have to import NumPy. Okay, so we're going to create our board. So it's going to be numpy.zeros 3, 3, 3. So this is going to be a matrix with 3 rows and 3 columns, and all of which are zeros. We're going to specify that these are all integers. Okay, so rather than like floats, because I should explain exactly what we are, how we're going about this. So the way I thought about this is, instead of filling the board with X's and O's, you could fill the board with like 1s and -1s, and then just check if when you sum like across the rows or across the columns, does it sum up to 3 or does it sum up to -3? Because if either of those two cases holds, then you have a winner. Okay, so let's then build the board. So for I, then x, y, enumerate nums, because nums is a sequence of numbers, and so when we enumerate it, I is going to be the index in this list, and then the second argument here, or the second variable here, is going to be the actual elements of moves, and each element is a list with 2 elements, and so we're going to store those 2 elements in x and y. Okay, so what we're going to do is x and y, so x is row, y is column. Well, I guess usually we use x for the x-axis and y for the y-axis, and in that case rows and columns. It doesn't matter. It all ends up being symmetric, so we don't need to worry about it too much. So board xy equals 1 if what? So whenever the player 1 moves, we're filling in a 1. And so player 1 is going to be the first, it's going to be the first element, which is index 0. Then you're going to skip 1 because the next one is player 2. Then player 1 will be the second element again, and then the fourth and the sixth and so on. So it will be 1 if I is even, meaning that when we divide I by 2, we get 0. But when we divide I by 2, we get no remainder. So that's what the percent sign is. It's division with remainder. And if this is not the case, then board xy will be -1. And just to be very clear, this is a, what we're doing here is this is just a simpler way of writing if I2 equals 0, board x, y equals 1, else board x, y equals -1. This is just a way of writing this all out in one line of code. Okay, which is neat. Okay, cool. So we have our board. Okay, so now we want to check if any of the rows, columns, or diagonals sum up to 3. And if so, then player 1 wins. Otherwise, player 2 wins. And so the way I'm going to do this, because we need to check the rows and the columns and the diagonals and stuff, we need to check these sums for both whether they sum up to 3 or when they sum up to -3. So I'm going to define a separate function here. So I'm going to call it check for winner. And I'm going to have x. I probably shouldn't use x. Let's use z. So z is going to be, in this case, it's going to be either 3 or -3. It's going to be what we want the entries to add up to in order to indicate a win. So if any, so we want to check if any of the columns add up to z. And so if any, then we'll do numpy.sum board axis equals 0. Is equal to 3. Okay, so what is this doing? Numpy.sum board axis equals 0, so it's going to take this board, which is a matrix. Axis equals 0 means that we're going to sum along the columns. So this numpy.sum, this whole thing I've highlighted here, this is going to give us a list of 3 elements. And each of those elements is going to be the sum of all the elements in a column. So the first element of this list will be the sum of the 3 elements in the first column. The second element of this list is going to be the sum of the 3 elements in the second column. The third element in this list is going to be the sum of the 3 elements in the third column. Okay. And so setting any this list equals 3 will return true if any of those 3 elements evaluates to 3. No, sorry, I'm thinking of the specific instance that we're looking for. But here we're thinking about z. So, if any of those 3 evaluates to z, then what that means is that this winning condition has been met in one of these columns. Okay. Otherwise, we need to check the rows, and the rows will be the same thing, except axis equals 1. We check if these are going to be equal to z. Okay. Now would be a really great time to remember the syntax for using multiple lines. Do you know, I'm just going to do this. I know this is probably not the best, neatest way to write this out, but I like using parentheses like this. So basically, you can use parentheses to continue things on multiple lines. Oh, but does this work for if clauses? Well, let's find out. Okay. Or, okay, so we've checked the rows, we've checked the columns. Now we need to check the diagonals. Now the nice thing about using NumPy is that we can use neat matrix operations. And one thing that's really common for matrices is adding up all the diagonal elements. And this is the sum of the diagonal elements of a matrix is called the trace. And so we can use numpy.trace to get the sum of all the diagonals on the board. So that would be these three that we see here. So we're going to check if this is equal to z. Or we need to check if this other diagonal is equal to z. And so we can't use trace because trace goes this way. But what we could do is we could flip the matrix and then apply the trace. And so we are going to use this neat function called, we're going to get the trace not of the board, but we're first going to flip LR board. Okay, so what is this doing? The first thing we do is we flip from left to right. And this is going to rotate it. I don't know which, I forget off the top of my head which direction this is. I believe this is going to rotate the matrix 90 degrees clockwise, because you'd go from left to right. So that would make sense. It's either that or counterclockwise, but it doesn't really matter because either way, whether you rotate this matrix clockwise or counterclockwise, the diagonal going, what do they call it? Do they use a name for it here? They don't. But this other diagonal, after rotating either clockwise or counterclockwise 90 degrees, becomes the original primary diagonal. Let's call it primary diagonal and secondary diagonal. The secondary diagonal becomes the primary diagonal after you flip it 90 degrees, and then you can apply the trace. Okay, cool. So that's the condition. So if any of these conditions are met, yeah, this is probably, you know what? I'm just going to make this one really long if statement. So yeah, let's just do this. Oh, this looks so bad. I'll look into the best way to write this out. So if any of these conditions holds, then we have a winner. Otherwise, we return false. Okay. So now we've created the board, and now we're going to use this function to check for a winner. So if check for winner 3. So this is going to check if this will check if any of the rows or columns or diagonals add up to 3. And if that is the case, then that means that player 1 wins. And so we're going to return A. Otherwise, if we check for -3, because we put in -1s whenever player B goes, then we will return B. Okay. What else do we have? So that's if we have a winner. The other scenarios are a draw and a pending. So how would we know if we're in a draw? Well, we get to a draw if we filled the board. So if the length of moves is 9, return draw. And by the way, I just thought to myself, could we just put this at the very beginning and like get draws out of the way really quickly, and you cannot because you can have someone win on the last move. So you need to make sure to check for draws after checking for winners. And then otherwise, if none of the other conditions have been met, then we are not pending, but pendering. Okay. So, yeah, this is our code. And let's submit it. And it doesn't work because nums is not defined. What is this list called? It's called moves. Where is nums? Here it is. And there we go. Well, it looks like it goes slowly. Maybe using NumPy is not the best thing here, or maybe this isn't the best implementation, but this is a solution and this does work. One thing that I will keep in mind that I do want to note here is this function here. So one thing I thought about is, does it make sense to have this function inside of tic-tac-toe? And you could keep it out. Like, there are arguments for keeping this outside of tic-tac-toe because that would make the tic-tac-toe function a lot cleaner. Like, there'd be less code within it, and so it would make it easier to read. And then this function could also be used in other areas. But that's actually a bad thing when you think about it, because the thing is, this check for winner, this is very specific to the game of tic-tac-toe. And so it makes sense to keep this inside tic-tac-toe so that it doesn't end up getting accidentally used somewhere else where it shouldn't be used. Because you could imagine, like, check for winner, like, what if you're writing code and this code contains a bunch of different games and you have a different function for each game? Then each function would need to have a different function within it for how to check for the winner. Now maybe you could call it check for tic-tac-toe winner and keep it outside, but this is fine. But it's worth asking these sorts of questions to yourself of, like, you know, how should this code be designed? But for this purpose, having this function in here is fine. And here you go. All right, so as for readability here, you could just, like, add parentheses and continue it on multiple lines. But one thing that I think would make this look neat is we can have a list of conditions, and this will contain every one of these conditions. So this will be a list of Booleans, and each Boolean is true or false based on whether the value, the corresponding value is true or false. And so we can check if any of the elements of conditions are true. And so that's the any function, if any conditions. So yeah, it takes in a list of Booleans and it returns 1 if any of those Booleans are true, and otherwise it returns 0. So you can do this, you can submit it just to check that it works, and it does. So there you go. Here's a solution. And here specifically, let me show the whole thing. Yeah, specifically here's a way to make this condition look nice. So yeah, there you go.